Welcome back to AI.Code.Cast. Today we're diving deep into a classic coding problem, and it's one that I think will resonate with a lot of our listeners.
Yeah.
It's the minimum refueling stops problem.
Oh, yeah.
Basically, we're trying to figure out
Mm-hmm.
the fewest gas station stops needed on like a road trip
Yeah.
to reach your destination.
Totally. So relatable, right? Like we've all been on those road trips. We're like, okay, do we need gas? Do we not need gas? Should we stop here? Like it's a real problem we face.
Yeah, for sure. And you've done some research on this problem, so I'm really excited to kind of unpack some of the clever logic behind these solutions.
Yeah, it's a great problem because it showcases some really powerful algorithmic techniques.
That's awesome.
But it's also something that, like I said, we can all relate to.
Right.
So you can really kind of grasp what's going on.
Absolutely. So we've got our car, right? Limited fuel tank.
Mm-hmm.
Destinations hundreds of miles away. We got gas stations along the way. Each one's got a different amount of fuel they offer.
Right.
Our goal is to find that absolute minimum number of stops.
Exactly.
So where do we even begin with this? Like, how do we even approach it?
Well, I think a good starting point is to think about like the most straightforward approach,
Okay.
which we often call brute force.
Okay, brute force. So that usually means like just trying every single possibility.
Yeah, basically. Just like throwing everything at the wall and seeing what sticks.
Okay, got it.
So in this case, imagine you're like planning out every single possible route combination of gas stations.
Yeah.
You know, stopping at this one, not stopping at that one.
Yeah.
And with hundreds of gas stations,
Oh, yeah.
this could be a nightmare to actually compute.
Right. So brute force is kind of out the window.
Yeah.
It's just, it would take forever, especially if we had like,
Especially long road trips.
yeah, cross-country road trip. You don't want to be calculating every single possibility. So there's got to be like a smarter way.
Yeah, there are definitely more efficient solutions.
Okay, so what's kind of the next level up from brute force?
So the research you shared highlighted two really clever solutions.
Okay.
One is dynamic programming,
Okay.
and the other is a heap-based approach.
All right. I've heard of dynamic programming.
Yeah.
I feel like it's one of those things that sounds very intimidating.
It can be, yeah.
But once you understand it, it's incredibly powerful.
Totally.
So can we maybe break that down, like using our road trip analogy?
Absolutely. So instead of like trying every single route,
Okay.
let's think about it a bit more strategically.
Got it.
We start by figuring out like how far can we go with 0 stops,
Okay.
just our initial fuel,
Okay.
and then how far can we go with 1 stop,
Right.
considering all the gas stations within reach.
All right. So we're kind of breaking the problem
Exactly.
into smaller chunks.
Yeah, you're breaking it down into smaller pieces,
Okay.
and then building up to the solution.
Right. Okay. So it's almost like we're building a bridge, right?
That's a great analogy.
One section at a time.
Yeah. You start with a small piece, and then you kind of expand from there.
I like that.
And that's really the core idea behind dynamic programming.
Okay.
You're breaking the problem down into these smaller overlapping sub-problems, and then you store the solution to those sub-problems so you don't have to keep recalculating them over and over again.
Oh, that makes sense.
It's like you're creating a roadmap
Mm-hmm.
to your destination, figuring out the best route based on where you can refuel.
Yeah. Okay. I'm starting to see like the elegance in this approach.
Yeah.
But how do we actually keep track of all these like sub problems and their solutions?
Right. So that's where this concept of a table comes in handy.
A table. Okay.
Imagine like a spreadsheet.
Okay.
Where each row represents a gas station,
Okay.
and each column represents the number of stops you've made.
Got it.
So each cell in that table
Yeah.
represents the furthest you can reach with that number of stops, considering all the gas stations up to that point.
So we're essentially like for each cell deciding,
Yeah.
is it better to skip this gas station?
Yeah.
Or refuel there based on how far it lets us go?
You're comparing those two options,
Okay.
skipping versus refueling,
Got it.
and you choose the one that takes you further,
Okay.
and you build this table up step by step,
Okay.
using the results from the previous calculations to inform your next decision.
I mean, this already sounds way more efficient than like brute forcing
Oh, absolutely.
every single route.
Yeah, you're avoiding so much unnecessary work
Yeah.
by storing and reusing those calculations.
Totally. And this efficiency, like how do we actually like measure that?
Right. So we talk about time complexity.
Okay. Yeah. Time complexity.
And in this case, the dynamic programming approach,
Yeah.
it takes O of n times k time,
Okay. O of n times k.
where n is the number of gas stations,
Okay.
and k is the maximum number of stops you're allowed.
All right. So time complexity for listeners who maybe need a refresher, what is that actually telling us?
So time complexity basically tells you how the runtime of your algorithm scales as the size of your input grows.
Okay.
So in this case, like if you double the number of gas stations,
Yeah.
the runtime of the dynamic programming solution is roughly going to double as well.
All right, got it. And then what about like space complexity?
Yeah.
It's all about like memory.
Right. Exactly. Space complexity is all about how much memory your algorithm uses.
Okay.
And for dynamic programming, it's actually pretty good.
Okay.
It's O of K.
Okay.
Which means the memory grows linearly with the number of stops.
So even though we're building this whole table, we're only really storing a limited amount of info at any given time.
Exactly. So, much more memory efficient than brute force.
Okay, that makes sense.
Which would have to store every single possible route.
Yeah, no, that makes sense. Okay, cool. So dynamic programming.
Yeah.
Starting to click for me.
Awesome.
But you mentioned this other solution, the heap-based approach. So what is that all about?
Let's dive into that next.
Okay, awesome. Okay, so this heap-based approach.
Yeah.
It sounds kind of intriguing.
Yeah.
How does it tackle this problem from like a different angle than dynamic programming?
So imagine you're actually on this road trip, right? You don't plan out every single gas station stop in advance, do you?
No, not really. Yeah. I mean, especially if it's like a cross-country trip.
Right. You're not going to know exactly.
I kind of just got to go with the flow.
Yeah. You drive till you need gas, and then you look for the best option that's available at that moment.
Totally.
And that's kind of what this heap-based solution tries to capture. It's simulating that real-time decision-making.
Okay. So how does that real-time decision-making actually like turn into an algorithm?
So we use a special data structure called a max heap.
Okay, a max heap.
Yeah, and basically what a max heap does is it organizes data so that you can always quickly find the largest element.
Okay, so in our road trip analogy, the largest element would be?
The gas station with the most fuel.
Okay.
So the max heap keeps track of all the gas stations you've passed.
Okay.
And it makes sure you can quickly find the one with the most fuel when you need to stop.
So it's like having like a super efficient co-pilot.
Exactly.
Who always knows.
Always knows where the biggest gas station is.
Where the biggest gas station is. That's awesome.
Even if you didn't plan to stop there.
Okay, so walk me through this step by step.
Okay.
So we're driving along.
Yeah.
Our fuel's getting low. What happens next?
As you're driving, you're keeping track of your current fuel level.
Okay.
Every time you pass a gas station, you add it to your max heap.
Okay.
And then when your fuel level drops below 0, meaning you need gas,
we look to our max heap.
Yeah, you go to your max heap.
Okay.
It tells you which gas station you passed has the most fuel.
Okay.
You refuel there, update your fuel level, and keep going.
See, this makes a lot of sense. Like, it's very intuitive. It's like how we would actually make decisions.
Yeah, exactly. It's like a more human approach almost.
Yeah.
It's not like this complex table or anything. It's just like...
Yeah, you're just reacting to the situation.
Exactly. You're reacting as you go.
Yeah, I like that a lot.
And the cool thing about the max heap is it does all of this really efficiently.
Okay.
So like adding or removing an element from the heap only takes logarithmic time.
Okay, logarithmic time. There's that word again. Can you remind me what that means?
Sure. So basically, if you double the number of gas stations, the time it takes to add or remove something from the heap only increases by a tiny amount.
Okay.
So it's not like linear time where it increases proportionally.
It just keeps going up and up and up.
Exactly.
Okay.
So even with tons of gas stations, the max heap can still make decisions really quickly.
That's really cool. Okay, so the heap-based approach seems really fast.
Yeah, and overall, the time complexity is O of n log n.
O of n log n.
Where n is the number of gas stations.
Okay.
So that's generally going to be faster than the dynamic programming approach, which was O of n times k.
Interesting. Okay, so the heap-based approach is faster. It wins on speed.
Yeah, generally.
Okay, but what about memory usage?
So that's where the dynamic programming has a slight edge.
Okay.
So with the heap-based approach, you need to store all the gas stations in the heap. Okay. So the space complexity is O of n.
Okay.
Which means the memory used grows directly with the number of gas stations.
So it's kind of a trade-off?
Yes, a trade-off.
Like the heap-based solution's faster, but uses more memory. Dynamic programming is a little slower.
Yeah.
But uses less memory. So it's really about like what's important for the specific situation, right?
It depends on what you're prioritizing.
Totally. Okay, so if speed is like...
If speed is your #1 priority, and you're not super worried about memory, heap-based is probably the way to go.
Okay, but if you're working with like a massive data set, and memory's like a big concern,
Yeah.
then dynamic programming might be better.
Even if it's a bit slower.
Even if it's a little slower.
Yeah.
Exactly.
Okay, cool. So there's no like one-size-fits-all answer.
Nope.
It's all about understanding the trade-offs.
It's about choosing the right tool for the job.
Yeah. Okay, I like that. All right, so now I want to touch on something that I think trips people up a lot when they're actually coding these solutions. Edge cases.
Oh, yeah. Edge cases are important.
Yeah. So what are some of the things that like people should watch out for?
So one common mistake
Yeah.
is forgetting to handle the case where you already have enough fuel to reach the destination.
Oh, right, yeah.
Like without stopping.
If we forget to check for that.
Yeah.
At the beginning, we might end up with a bunch of unnecessary stops.
Exactly. You could end up overcomplicating things.
Right. Okay, so what else?
Another thing to think about
is what happens if you reach a gas station with an empty tank?
Oh, that's a good question. Can you still refuel?
Yeah.
Yeah.
In real life, you'd be stranded. I'm guessing in this problem...
Yeah, in this problem, you can typically, you can refuel even if you arrive with 0 fuel.
So it's like you're coasting in on fumes.
Yeah, think of it like that.
Okay.
You're just making
Okay, so we need to make sure that our code can handle that situation.
Exactly.
Okay. What else?
We always want to test your code thoroughly.
Oh, yeah, of course.
Including those edge cases. Like, what if the list of gas stations is empty?
Oh, yeah.
What if the destination's unreachable no matter what you do?
Right, like you always want to make sure you're not just testing the happy path.
Exactly. Test all the weird scenarios.
Where everything works perfectly.
Yep. Make sure your code's robust.
Yeah.
And can handle anything you throw at it.
Totally. And it strikes me that this minimum refueling stops problem isn't just about road trips, right?
Right. Like it feels like the logic could be applied to other problems.
Absolutely. It's a great example of algorithmic thinking.
Okay.
That you can apply in different areas.
So like what kind of other areas?
So think about like resource allocation.
Okay.
You have a limited budget. You need to decide how to spend it.
Yeah.
To maximize your output.
That's like our fuel budget.
Exactly. It's like your fuel.
And trying to reach our destination.
And you want to reach your goal with that limited budget.
I like that. What else?
Or like scheduling tasks within a certain time frame.
Yeah.
That's like optimizing those fuel stops along a route.
Yeah, making sure you can get everything done.
Making sure you can fit everything in.
Within that time constraint.
Exactly.
Okay, cool.
Yeah.
So it's like this problem that seems so specific can actually teach us about problem solving more broadly.
It's all about the underlying principles.
That's what I love about coding.
Me too.
It's awesome. Okay, so I think we've covered a lot of ground today.
I think so.
We explored the minimum refueling stops problem. We tackled dynamic programming.
Yeah.
The heap-based solution. Talked about edge cases and broader applications.
Yeah, it's been a good deep dive.
It has been a good deep dive. So as we kind of wrap up here, what are some key takeaways you want our listeners to remember?
I think the biggest one is that there are often multiple ways to solve a problem.
Okay.
And the best solution depends on the specifics.
Right. So like dynamic programming and heap-based approach are both valid ways to solve this.
Exactly. They both have their strengths and weaknesses.
Yeah, totally. And I think another key takeaway is that understanding the logic is just as important as being able to write the code.
Absolutely.
It's about
the thinking process.
Right, yeah, that algorithmic thinking.
Yeah, being able to break down the problem.
Yeah.
Come up with creative solutions.
That's going to help you no matter what you're coding.
Exactly.
Awesome. Well, I think that brings us to the end of our deep dive into the minimum refueling stops problem.
It's been fun.
It has been fun.
Yeah.
So we hope you found it insightful.
Yeah.
Maybe even a little inspiring.
Yeah. And remember, coding is all about learning and discovery.
Totally. Keep practicing, keep experimenting.
And have fun.
And most importantly, keep having fun.
Yeah.
All right. Thanks for joining us on AI.Code.Cast.
Thanks, everyone.
Until next time, happy coding. Okay, so we talked about edge cases, right? What are some of those common pitfalls when we're actually coding up these solutions?
Yeah, so one common mistake is forgetting to handle the simple case where you already have enough fuel to reach your destination without stopping at all.
Oh, that's a good point. Yeah, you can get so caught up in the logic of refueling that you forget to just check if you even need to stop.
Exactly.
At the beginning, and then you end up with all these extra stops that weren't even necessary.
Yeah, totally overcomplicating things.
Okay, cool. Anything else to watch out for?
Another one is what happens if you reach a gas station with an empty tank?
Oh, yeah. Good question. Can you still refuel I mean, I know in real
Yeah,
life,
you'd be stranded. But in this problem,
we're assuming we can magically refuel even with zero fuel left.
right, it's like you're coasting in on fumes, you just barely make it.
Okay, so we need to make sure our code can handle that. Arriving at a station with zero fuel and still be able to refuel.
Exactly. And of course, like always, um, you want to test your code thoroughly
Oh, yeah, for sure.
with all those weird edge cases. Like, what if the list of gas stations is empty?
Oh, right. Yeah, good point.
What if the destination's like unreachable no matter what you do?
Yeah, we got to test those scenarios, not just the happy path where everything works perfectly.
Exactly. Got to make sure your solution's robust, can handle all those unexpected situations.
Totally. It strikes me that this problem, this whole minimum refueling stops problem. It's not just about road trips, right?
Yeah, it's way more than that.
It feels like this logic, this whole idea, could be applied to so many other problems.
Oh, absolutely. It's like algorithmic thinking. You can apply it in lots of different areas.
Like what kind of other areas? Give me an example.
Okay, so think about resource allocation, right?
Hmm.
You have a limited budget and you have to make choices. How to spend it to like
Hmm.
get the most output, maximize what you can achieve.
Oh, yeah. That's just like our fuel budget
Yeah,
and trying to reach the destination.
exactly. It's all about using your limited resources wisely.
What else? What other examples can you think of?
Let's see. What about scheduling tasks?
Okay, yeah, tasks.
Within a certain time frame, like you have a deadline.
Right.
That's kind of like optimizing your fuel stops, making
Mhm.
sure you can complete all the tasks before time runs out.
Yeah. Within that constraint, that time constraint. Okay, I love that. So this problem, that seems so specific, right? Like, oh, it's just a road trip. It can teach us about problem solving in general.
It's all about those underlying principles, the core ideas behind the solutions.
That's what I love about coding. You can learn so much. All right, I think we've covered a ton of ground today.
Yeah, I think so too.
We explored this whole minimum refueling stops problem. We tackled dynamic programming, the heap-based solution, talked about edge cases, broader applications. What are some of the key takeaways? The things you really want our listeners to remember.
I think the biggest one is that there are, usually multiple ways to solve a problem.
Mm-hmm.
And the best solution, it really depends. It depends on those specific constraints and your priorities, what's most important in that situation.
Yeah, so like dynamic programming, heap-based approach,
Hmm.
they're both valid ways to solve this. They just have different strengths and weaknesses.
Exactly.
And, I think it's important to remember understanding the logic behind those solutions is just as important as writing the code.
Totally agree. It's about the thinking process.
It's that algorithmic thinking, right, that's going to help you with any coding challenge.
Absolutely, yeah. It's all about breaking down the problem, being creative.
Awesome. Well, I think that brings us to the end of our deep dive into
Yeah.
this minimum refueling stops problem.
Yeah, it's been a good one.
It has been a good one. Hope you found it insightful, maybe even a little inspiring. And remember, coding is a journey. It's about continuous learning. It's about discovery.
Keep practicing, keep experimenting, and most importantly, like, have fun.
Yeah, have fun. All right, thanks for joining us on AI.Code.Cast.
Thanks, everyone.
Until next time, happy coding.